Hello everyone, we're going to get started with part 4 of module 2. And before we get started with ideal gas, I wanted to do an extra example of an actual system being heated and sort of looking at how to use the tables to figure out this type of problem. So to get started, we're going to do this example problem, which is problem 357 in your book. It's a problem in your book, so if you want to look at the problem, you can, but the problem is copied right here. And then we'll go on to studying ideal gas and what that actually means and how we can use it within our course. So in this example, we have 10 kilograms of R134A, and the 10 kilograms of R134A fill a 0.7 meters cubed weighed piston cylinder device at a pressure of 200 kilopascals. The container is now heated until the temperature is 30 degrees. Determine the initial temperature and final volume of the R134A. So the first thing we want to do in these kinds of problems is to write down all of our values, and I'll show you how to sort of write down those values. But before we get started, I just want to do a little diagram of what we have in terms of our piston cylinder. So our piston cylinder looks something like this, and pretty simple device. And we know that we have R134A, and we're told that we have 10 kilograms of R134A and that the volume is equal to 0.7 meters cubed. Okay, and we're given a little bit more information than that. We're also given an information that we have a pressure of 200 kilopascals. So the pressure of 200 kilopascals is essentially created by making a pressure that's outside of the piston cylinder of 200 kilopascals. But the pressure inside is exactly the same pretty much because we have a piston cylinder device that's weighted and the weight is equivalent to 200 kilopascals of pressure. Now, in our problems, what we're going to be doing when we have a problem where we have a change is we're going to define how many states we have. So in this problem, we have an initial temperature and a final volume. And it seems to be like there is one action that is now heated until 30 degrees. So anything before this sentence here is a first state of our system, and then anything after that sentence is a second state. So what we're going to do is we're going to write state 1 and define everything that we have at state 1. And the first thing we can see is that our mass is equal to 10 kilograms. We can also stay at state 1 and we're going to put volume 1, mass 1. Volume 1 at state 1 is equal to 0.7 meters cubed. And we're also told that pressure 1 is equal to 200 kilopascals. Now, it says the container is now heated until a temperature of 30 degrees. So in a second instance, we have a second state where the container is now heated to a temperature of, so a state 2, we're told that temperature 2 at state 2 is equal to 30 degrees Celsius. We also know from the fact that it's a weighed cylinder at a pressure of 200 kilopascals, and we're told that there's no change in pressure. And since it is a piston cylinder device and we're just going to add heat to it, the pressure stays constant because the piston is free to move. The piston being free to move means that the pressure stays constant. And lastly, we also know that our mass is unchanged. Mass 2 is equal to mass 1. Okay, we have a control mass system. The system is completely closed and does not let mass escape, except if it tells us mass escapes, but in this case it doesn't. So that's the definition of state 1 and state 2. Now, these states are incomplete in order to find the initial temperature and final volume, right? We have pressure, volume, and we're missing temperature 1, and we're missing volume 2 essentially. And that's what we're trying to find in our question. So anytime we have a question with a piston cylinder, and most of the questions in this class are going to require us to find other variables within a state outside of the ones given. Okay, so how are we going to find the initial temperature? So let's focus on, let's do part A is finding T1. How do we find T1? Well, we're told we have R134A, so we're going to be using, we know the tables for R134A. Anytime you have water or R134A, you're going to want to use the tables. There is no reason to use an equation if you have tables. Tables are the most accurate way of getting a value for R134A. It's direct experimental values that you're just interpolating. So what we're going to do is we're going to use a table. And in order to find temperature from the tables, we need two values. Remember, our tables correlate between pressure, specific volume, and temperature. So we need two out of those three to find the third one. The first one is pressure. The second one is specific volume. Can we find specific volume from our existing volume? Yes, we can. Specific volume is equal to volume over mass. So it's equal to 0.7 divided by 10. So our specific volume in our problem is equal to 0.07 meters cubed per kilogram. This is the specific volume of our fluid at the initial point. And from there, we can write down that P1 is equal to 200, V1 is equal to 0.07, and we can go to our tables. And we're going to choose to go to table A12 because table A12 is for the saturated mix with pressure. So it's a pressure table for the saturated mix. And remember, we always start with the saturated mix to figure out if our system is a saturated mix or not. So we're going to go to table A12. So let me just go to table A12. So we're going to shift to table A12. There's annotations from the earlier part, but ignore the annotations for now. So let me just erase them so that we start with a blank slate. And we're told that we have a pressure of 200 kilopascals, so we're going to go to this line right here. And we have, since we have a volume, so our specific volume is 0.07, we're going to compare that specific volume and figure out if we're within the saturated mix region or outside. Turns out that we are inside the saturated mix region. So we're in between. 0.07 is lower than Vg and is higher than Vf. So going back to so we can say that from table, V is between Vf and Vg. Therefore, we have a saturated mix. Now, it doesn't ask us to figure out if we have a saturated mix, but since we do have a saturated mix, we know that inside the region of the saturated mix, if we draw our PV diagram and sort of like a constant pressure system, we know that if we're inside the saturated mix, our temperature is going to be constant, and our temperature is going to be Tsat. So T1 is equal to Tsat, which from our table is equal to minus 10 degrees 0.09. So our Tsat is going to be equal to minus 10.09 degrees Celsius. And so that's the answer to the first part. Now, we add some heat to the system, and we're told that the system heats to 30 degrees Celsius. So we know that state 2 has a pressure 2, which we already wrote above, of 200 kilopascals. The pressure does not change because we are in a piston cylinder assembly that is free to move. And temperature 2 is equal to 30 degrees Celsius. Now from the tables, we can figure out what our V2 would be, which in turn, after that, we can do volume 2 is equal to mass times specific volume 2. So let's try and find specific volume from the tables. So going back to, let's go to table A12 again. And from table A12, we can see, and I'll just write it here, that our temperature 2 is greater than Tsat. Therefore, we can say that we have a superheated vapor. Okay, we know that we have a superheated vapor because our temperature is greater than Tsat, which means it has already boiled. Therefore, we can go to table A13, which is for superheated refrigerant. And we're going to find the point where pressure is equal to 200 kilopascals, which is right here. So we're going to use this box right here. And we're going to try and figure out what our specific volume would be. Now, we know that our temperature is 30 degrees, so we have it right here. And to find the specific volume is in this first column. So the specific volume that we're interested in is this one right here. No need to interpolate this time. So we have a specific volume of 0.11874. So I'm going to write that over here. So our volume 2 from table A13, volume 2, or specific volume 2 is equal to 0.11874. And following that, we can multiply by the mass, which is 10 kilograms, and we finally get 1.1874 meters cubed in this case. Now, what if we were to draw this on a PV diagram? So let's say we have a PV diagram. How would we draw this change from point 1 to point 2? Well, we just plot the values. So we know that pressure 1 is 200, and we know that volume 1 is, so volume 1 is equal to 0.7. So we have 0.7. This is 0.1. And then we know that the pressure stays constant. It stays at 200, and our second point is 1.18. So our volume here would be 1.1874. And so we see that our process from 1 to 2 would follow a straight line from 1 to 2. Now, if we were to add our boundary lines for our boundary lines that define if we have a saturated mix or a superheated region, it would look something like this. So we would start as a saturated mix, and as the system is heated up, we go outside of the saturated mix, the pressure stays constant and the volume increases. Okay, so that's a little bit of an explanation of how that would work. Okay, if we wanted to draw the graph of what actually happened. Okay, so that concludes the example. So now let's go on to ideal gas equation of state. So we're going to talk about the ideal gas equation of state. And the reason we're talking about the ideal gas equation of state is that so far, we have found pressure, specific volume, and temperature using tables. For R134A and for water. Now, instead of using tables, we can also use something called an equation of state or equations of state. There's multiple equations of state, but we can use equations of state instead. What equations of state are simple equations that can help us find values and relate pressure, volume, and temperature, for example. So one of these equations of state is the ideal gas equation of state, and it's the simplest equation that we can have. And this equation states that PV, which is specific volume, is equal to RT, where P is absolute pressure, V is specific volume, R is a gas constant, and this gas constant is specific to the gas used. So it's the units of the gas constant are kilojoules per kilogram Kelvin. And this is different for different gases. Okay, so different gases have different gas constants. And then finally, T is absolute temperature. And remember, absolute temperature is in Kelvin, not in Celsius. Okay, this equation can also be written as PV is equal to mRT. Just by substituting for specific volume, you can have a capital V is equal to mRT. Okay, that's another way to write it. Now, the chemical version of the equation that uses the universal gas constant, which is a universal gas constant between all the gases, is PV is equal to nRUT, where RU is the universal gas constant. In this class, we're going to focus mostly on using R, which is the gas constant specific to each gas. So just to make sure that everybody's okay with this, I'm going to write specific to each gas. And R can be found from RU divided by capital M, which is molar mass. Okay, just to get a little bit of background on this. Okay, but we're going to mostly use this first version of the equation at the top, or this equation right here. And in our appendix, we actually have values. In appendix A1, we actually have values for the gas constant for different gases. So it makes it very easy. We can just find the gas constant for all the gases to the right of the red line. So that's going to be very useful. Now, the ideal gas constant. Can we use it for air? Can we assume air is an ideal gas? Well, turns out that the ideal gas constant works well for air. So instead of using the tables for air, the ideal gas constant would work pretty well. And the tables for air would require you to have actual tables for air, which we do have, but only in limited capacity. So it does work well for air in general. Now, how does it work for water? Can you use it for water? For water, it is actually a little bit more challenging to use because water is not just a gas. Water can be a fluid and water can be a solid. Can you use ideal gas law to model the work of a solid or a liquid? No. You can only use it, and really, it's going to be very rare that you use it with water, but you could only use it when it's a vapor. If water is a vapor, you could use ideal gas. But would you or not? You probably wouldn't because you have the tables. So it's usually better to use tables. Okay, it's a lot better to use tables and it just makes more sense because you get actual experimental data and not data from an equation um, that is an approximation of what is happening. Okay, now the ideal gas equation also works well in general for low density and low pressure gases. So if a gas starts being very compressed and has a high density because it's, for example, very cold or there's a lot of pressure on the gas itself, the ideal gas equation starts having more and more errors. So it's a little bit of a compromise and you have to be careful when you're using it. But for most gases in this class, we will be able to assume ideal gas. And we're going to study in this chapter, and this is the last part of the chapter, we're going to study how to measure deviation from ideal gas if and is it needed or not. Okay? But before we do that, let's look at I want to look um, at two different states and looking at a mass. So let's say we have a piston cylinder assembly and we have 1 kilogram of air in state one, and then we still have that kilogram of air in state two, and maybe we just added heat between the two so we have a different temperature or different system, but we still have the 1 kilogram of air. Okay, now what is nice about the ideal gas equation is, let's say V, so if we have heat, volume has increased, and maybe temperature has increased as well, okay, but definitely volume has increased. And if we have a fixed mass system, so now we're looking at air, we're not looking at water R134A. If we have water R134A, we can just use tables to find pressure volume, and temperature if we have some given parameters. But the nice thing is that we can write an equation for state 1 and state 2 now. So if we use the ideal gas equation for air, we can say that P1 V1 is equal to mR T1. Okay, and for state 2, we can also write an equation. We can say that P2 V2 is equal to mR T2. Now, notice that the mass is constant. So we can rearrange this equation to say mass is equal to P1 V1 over R T1. And here the mass is equal to P2 V2 over R T2. Now, the R is also the same. So the gas constant, the gas hasn't changed. So the R is the same between the two gases. And so now we can simplify the equation and we can make them equal to each other. We can make these two equations equal to each other. They are equal to each other. They're both defining the mass. So we can say in a fixed mass system that P1 V1 over T1 is equal to P2 V2 over T2. So if we know the first state and we know some values for the second state, we can find our temperature or our other values that we're looking for, either pressure, volume, or temperature. And we're going to be doing an example so that it is clear to you. Now, if you have water or R134A, you always use tables whenever possible. Do not use ideal gas for water, especially if it's liquid, okay? But do not use ideal gas equation for water. Every semester, there's one or two people that in the first or second quiz or in the midterm, they will use ideal gas equation for water R134A instead of using the tables, and they essentially get a 0 on that problem. For air or gases, in this class, unless stated otherwise, we use ideal gas. Okay, so we use the ideal gas relations for air or gases unless stated otherwise. And in this chapter, we're going to study how we can measure the deviation from ideal gas. But once we've studied that, we don't have to look at it anymore moving forward. Okay. So let's do a quick example of how we can apply ideal gas to a real world problem. So let me just cut here so that we have a new page. So we said that P1 V1 over T1 is equal to P2 V2 over T2. And let's look at what would happen if we have a temperature rise in air in a tire during a trip. Okay, so let's look at a temperature rise in air during a trip. So before a trip, we're told that the pressure gauge, so it's a gauge pressure, the pressure that you measure on your tire, is equal to 210 kilopascals. And this is of a car tire. And we're told that after the trip, the pressure gauge has increased to 220 kilopascals. Okay, probably because of a little bit of the heat. A little bit of heat went into the tire while it was driving, or the temperature of the tire changed, or something happened to the tire for it to increase in pressure. Now, we're also told that pressure atmospheric is equal to 95 kilopascals. Okay, and that's the atmospheric pressure. And remember that gauge pressure is pressure added in addition to the atmospheric pressure. It's not the absolute pressure. So we usually have to find the absolute pressure in thermodynamics. We're also told that the temperature of air was 25 degrees before the trip. And that's the temperature of the air inside the tire. And our goal is to determine the temperature after trip. So we can essentially write this as P gauge 1, P gauge 2, okay, and then this would be T air 1 and then T2. And we're trying to find T2 just to make sure that we define the states. So some of the assumptions that we're going to make in this problem, and these are assumptions that you can write yourselves, and sometimes they're also given to you, but most of the time you make the assumption yourself. So we're going to assume that air is an ideal gas. And we're also going to assume that mass of air in tire does not change. Okay, we're told no information that the mass is changing, so we're just going to say that it does not change. And since the tire is a pretty rigid system and the pressure hasn't increased that much, we're also going to assume the volume is the same. We cannot really assume that, but in this case, they don't give us more information on the volume. So we assume that the tire is a rigid body and it's not going to change in volume a lot. And that's actually really true from a real tire. The tire, once it's inflated, does not change much in volume inside. The volume of air inside does not change much. The only thing that changes is the pressure of the air inside the tire once it's in full shape. So we're going to define state 1 and state 2, just to summarize. So state 1, we have that pressure 1 is equal to 210 kilopascals. And remember, our pressure is always absolute in thermodynamics. So we're going to add the 95 kilopascals here directly so that we have the actual right pressure immediately, 305 kilopascals. We know that temperature 1 is 25 degrees Celsius. We know that V1 is equal to V. We're not given the volume, and mass 1 is equal to M because we're not told the mass as well. In state 2, we're told that pressure 2 is equal to 315 kilopascals. And we're told to find T2, and we're told that mass 2 is equal to mass 1, and V2 is equal to V1 from our assumptions. Now, how do we go about finding temperature 2? Well, we're going to use the equation we just derived before. P1 V1 over T1 is equal to P2 V2 over T2. And from this equation, we know that V1 and V2 are the same. So they're just going to cancel out. So we're left with P1 over T1 is equal to P2 over T2. And now if we rearrange the equation, we can isolate T2 and we can say T2 is equal to P2 over P1 times T1. Now, what temperature are we going to use for T1? Remember, we have to use absolute temperature for ideal gas. So we need to convert our temperature to Kelvin. So we're going to have 315, which is our absolute pressure, over 305, multiplied by 25 degrees plus 273 to convert it to Kelvin. And we're finally going to get an answer for T2 of 307.8 Kelvin, which can be also written back into Celsius if you want to. The temperature in Celsius would be 34.8 degrees Celsius, just by subtracting 273. Okay, so that's an example of how to use the ideal gas law in a somewhat realistic example in real life. Now, moving forward from this, we're going to be looking at, can we measure deviation from ideal gas behavior? So the next thing we're going to be looking at is, can we measure deviation from ideal gas behavior? And the idea here is that we're going to introduce a correction factor called the compressibility factor. Now, just as an information, this is not going to be, anything on ideal gas is not going to be on quiz 1. So you will not have to know about ideal gas on quiz 1. So you don't have to prepare for quiz 1 with this, but you do need this for the subsequent chapters that we will be studying. This concludes part 4 of module 2. And in part 5 of module 2, we're going to be looking at if we can measure the deviation from ideal gas behavior. And we're going to be introducing a correction factor called the compressibility factor. So I'll see you in part 5 for that part, which will be the last part from this module.